Okay.
It's not the first time.
Okay, so it's a pleasure to have Lukasz also from University of Warsaw. And he is going to tell us about information geometry of Bayesian, that correct? Bayesian,
Yeah.
Bayesian updating and replication. Classical section.
Yeah.
Please.
Yeah. Hello. Thank you everyone for coming here and for giving me the opportunity to diverge a bit from the usual subject. Basically, don't worry, don't be scared. I'm starting with a gentle introduction to
Just like Tom.
maybe not that elementary, but you know, I hope find themselves when it comes to this. So basically what we aim to do was to find some formalized, more or less categorical setting for modeling the system that gains knowledge autonomously, not in the sense of AI or large language models, but more or less in the sense of how we would like to model some philosophical notions of gaining knowledge. That's why the word epistemic appears here. So yeah, when it comes to mechanism that we've observed, when it comes to gaining knowledge, is Bayesian updating, which is pretty standard because well, you have the whole branch of statistics called Bayesian inference. And in short, it means that, okay, I get new evidence, I change my decision making. And the other one is data replication, because more or less we can gain knowledge by observing the same random phenomena happening independently many times. And we try to use these two notions and incorporate in some way the heuristics that people in chemistry, biology, and thermodynamics use when they reason within their domains. And the principle that pops up the most is named after James, whose principle is, if I remember correctly, the most directly and widely used in the realm of statistical mechanics. So, okay, the plan for my talk, I'll try to be brief, is first some motivation, then what happens in the realm of probability, and then how, in short, this statistical phenomena translate into geometric world. And I'll be quick enough. I'll finish with a nice example from biology. So, okay, first of all, what do I even mean by statistics, and why I'll be making a quick jump from the usual notion of random variables as measurable mappings from measurable space to some convex set to surjective affine maps. Well, to put it shortly, because of the existence of somewhat universal random variable that embeds the space of elementary events into the space of probability measures by simply assigning to each omega delta measure focused on the singleton omega, we can translate uniquely the information carried by a measurable map F to a functional on measures that is simply taking expected values of this random variable, and the probabilistic measure is the variable that varies through it. That's why zooming is the space of probability measures on our sigma algebra F. Okay, so now that we made the jump, so that we start from probability spaces and we go on into some convex sets, we would like to model somehow what happens with our knowledge and ability to make decisions when we leave the space of true probability distributions and look at some, let's say, average information. And basically, in practice, we never see the beginning of this process, but still we get some reasoning power from a data aggregated near the end of this chain. But there are two problems with using this knowledge in reasoning. Well, in the process of this data aggregation, two things may happen. One is that we simply lose some knowledge through this process. And the other one is that even if we don't lose any information, it may be distorted and hard to decipher. So to fight these two phenomena, we would like to have some additional information that will help us decide, okay, how to recognize that this data is distorted or not, and how to recognize what we've lost. And basically, this the answers to these conundrums will be looking in the realm of geometry, and to somehow come back to the land of pure knowledge, we would like to have a way to return from this process of data aggregation backwards through some chain of sections associated to each of these, let's say, random variables, even though a random variable should only be a name given to a map whose domain in the space of measures. But that is just a fun fact. So, okay, we know what we have. We know that we're looking for geometry, for something in the realm of information geometry. So how will we approach this process of gaining knowledge? Well, both replication and Bayesian revision should come from some kind of group or semi-group action. And these symmetries should reinforce our certainty when it comes to possessed knowledge. And that is why we decided to couple them together and give it a name reinforcement. And basically, we will try to convince you that at the level of probability spaces, there already is a reinforcement group that acts on probability distributions, but that its true nature only shows itself when we make jump to, let's say, openly geometric realm. And moreover, that the jump from the realm of probability, the realm of geometry, will be in fact factorial. So, Okay, let us start with the realm of probability. And in short, the schema that will show itself again and again is that we will, from slide to slide, slowly build, let's say, a ladder of more and more complex structures. So, okay, for the start, we have just a plain probability space. So, of course, a set, sigma algebra owner, and probability measure on that sigma algebra. And we will look for starters at two categories. The first one is just probability spaces with measure preserving Maszczyk morphisms, i.e., if we have a map pi, then the condition imposed on the measures is that the one in the codomain is the direct image of the one in the domain. And the other one that we would like to jump into is the category of convex sets and morphisms being surjective affine maps. So, okay, if we define an assignment to a probability space, something like that, i.e., the set of all probability measures that are absolutely continuous with respect to our chosen measure P, and that with random-Nikodym derivative is essentially bounded with respect to P. This will, in fact, be a good candidate for our simplex of probability measures. In short, the weird condition is the one stating that the random-Nikodym derivative has to be essentially bounded. It is here simply to enforce the fact that the random-Nikodym dominating relation, i.e., this one, would be nice if it was equivalent with the dominating relations coming from convex geometry. And if we were on simplex of finite dimension, this is for free, because for now we are in the general case, something like that has to be adopted so that there's no question regarding that. And for an morphism, we simply put the direct image as the value of our functor delta on this measurable map. And because we restrict ourselves only to measures that are absolutely continuous with respect to P, the direct image will, in fact, be a surjective affine map. And it's a simple calculation showing that this assignment creates a functor from probability spaces to convex sets. So for now, we managed to gain a simple structure from probability spaces. We advanced to something that we'll think of as a simplest, even though it is infinitely dimensional, and for now, at least without any topology on it. Okay, so next step, we would like to get some action on acting on our structure, and it is possible to define quite canonically the Bayesian action on the simplex of probability measures. So the group that we'll take into account are the invertible essentially bounded functions with value-wise multiplication that's group as group multiplication. It was a bit silly, and that acts on the probability measures via this formula. This is in fact a group action, and it is induced from the linear group action on finite measures. And when we restrict ourselves to probability measures, the nature of this action is projective, but for today it is more or less a fun fact. But what is quite important, and I've realized way too late, taking into account how long I spent with this setting, given memorable map pi between probability spaces, it naturally induces a group homomorphism between these groups assigned 1 to probability measure P1 and the other to probability measure P2, simply via pullback, which gives us our next step in gaining structures. So now we have convex synthesis of probability measures.
Wait, Lukasz, but
Yeah.
this is the graph of SQ2 graphs is drawn.
I think this thing look a bit different, but maybe very
We
slightly.
found a connection.
Yeah, there may be something in it, but I won't risk it today. We can talk about it later. Okay, why do I say that something defined like this should be named Bayesian action? Well, if you open the probability textbook, you would see that, yeah, something similar to that appears when you have Bayesian theorem for continuous random variables, but the convincing argument is even more elementary, because everyone doing school encountered the classical Bayes theorem for classical probability, and in fact this formula here can be easily recovered by group, by the action of a certain group element acting through what I called previously Bayesian action. And that is why we gave it that name. So our next step is to look for this replicating action. And while thinking of how to model Bayesian updating was pretty easy, thinking of how to tackle data replication was easy when it came to intuition, but pretty troublesome when it came to technicalities. That is why I give you now the rather technical definition of what it means for a map to be random-Nikodem differentiable instead of, the two measures being random-Nikodem differentiable with respect to each other. It is a technical definition that we will not spend too much time today, but if anyone's interested, it is available in the slides. Why it was important was because we wanted to get a fibered product that would, through fibered powers, model the behavior of exchanging a random event for a series of independent occurrences of this random event. And if we use the usual notion of amorphism to construct a fiber product, we would get the so-called measure extension instead of something that would, replace an event by a series of events. Either way, we've calculated how in this paradigm the explicit formula for probability of fiber product will look like, and it allowed us to create appropriate fiber powers of both our space of elementary events and measures, which leads to a formula, well, it's called R because of replication, that behaves in this manner. And it is really tempting to say, okay, this guy here, he has a really nice interpretation from the probabilistic side, simply because, okay, it comes from the projection from fiber powers. And this is what allows us to interpret it as this exchange of random event for a series of independent occurrences of that event. And the explicit formula gives us simply taking powers of certain densities, randomly derivatives, and normalizing the measure. And it is quite tempting to jump, okay, but this kind of operation has sense for not only natural numbers, but much more. But we decided to restrain ourselves on that front, because even though it is quite easy to prove that this formula for RK behaves as I won't say monolith action of natural numbers, but we exclude zero from this. But we can extend it uniquely because of this commuting diagram to the action of positive rational numbers. And okay, now is again the time when we would be tempted to say, okay, it's just now we have the action of rational numbers, we'll just extend by continuity, but here's the catch. For now, on the simplest of probability measures where this guy acts, we don't have any topology. So we should restrain ourselves for one more moment when it comes to extending this action to real positive numbers from rational positive numbers. And yeah, I have to say that here's a mistake I forgot to fix, because, okay, we managed to extend our group action from these invertible essentially bounded functions to the action of a semi-direct product of these functions and positive rational numbers. But in fact, this morphism here shouldn't really be identity, but that will come again in the geometry program, just so that there will be no lies during this talk. This is my bad. This slide should be fixed. And the last thing that we'll use a bit later is the last thing that I mentioned during the plan of tackling this problem, because this is basically all the structure we managed to identify at the level of probability spaces. And we want to jump to realm of geometry and have some means of doing that. And to do that, we will incorporate something that is well known in the realm of statistics, which is the Kullback-Leibler divergence. It is used in many contexts, but what is important for now is that it is a function given by such a formula, and it can be defined for all measures where the first argument is absolutely continuous with respect to the second one, and to make everything work out smoothly, we want to restrict the domain of the second argument only to measures that are mutually absolutely continuous with respect to our chosen measure P, so that to gain a bit of generality, but to not forget that, yeah, the data that was given to us at the very beginning was the space with distinguished measure. And a lemma that will play unbelievably important role later on, when we will restrict ourselves to finite sets as our spaces of elementary events, is that if we have a map that is surjective as a map between these finite spaces of elementary events, and we induce from it direct image which acts on honest to God M simples and N simples that is well known to everyone, then the minimization on fibers of this map acts exactly in this manner. This may look pretty trivial and maybe even innocent, but this is exactly the lemma that guarantees that the Kullback-Leibler divergence may be reinterpreted as a functor from, let's say, the category that lives fully in the realm of probability to the category that breathes and lives not only geometry, but information geometry. So now, to look at the other side of our puzzle, we need to get some standing in the realm of geometry that we want to jump into. So, in short, the geometrical objects that will be of our interest are triples, where X is in general convex polytope, but it's much easier to look at each open strata of convex polytope at a time and say what's happening on this open strata, and then say that, okay, and it glues all together just okay at the very end. We need distinguish smooth, strictly convex function, of course, because the convex polytope is stratified. It will also need to be stratified, and because it is strictly convex, it can generate a Riemannian metric. Of course, again, stratified by simply taking Hessian of this thing that from now on I shall address as either information potential or metric potential, because of the potential that generates metric through Hessian. And for morphisms, we still stick to surjective affine maps. Just a heads up, we tried to get rid of this assumption that the maps need to be surjective, and it didn't end well. In short, there is a moment when you encounter the fact that, okay, if this model was to be correct, every survey should be absolutely true, and it's impossible. Therefore, we need to restrict ourselves to the surjective maps, and which may be a bit surprising at the first glance, a really important role in this geometric side of things will be played by the Legendre dual coordinates of our convex sets. So, okay, let's go further. When it comes to the relation between our information potential and its Hessian metric, well, of course, this potential is not uniquely defined by the metric it generates, because if we perturbate it by some affine function, then, well, second derivatives will kill the affine component, and the metric generated will be the same. And that is why we incorporate these possible perturbations here as gauge action, because yeah, it really resembles the gauge that you may encounter.
Gauge action now a point of contact.
Yeah. Okay. So now, previously we had achieved some more or less canonical group actions in the realm of probability. So where to start to define something similar in this purely geometric realm? Well, thankfully, if we look at the gradients of the potentials of our metric, they span Lie algebra, and moreover, this Lie algebra has really nice maximal normal subalgebra, which in fact is spanned by, I use X here, by the G gradients of the affine gauge functions. And if we calculate the formulas directly, we would see that, okay, these algebras have a really nice description in terms of Legendre dual coordinates, i.e. these the big algebra G is generated by the derivations in dual coordinates, and the Euler field in dual coordinates.
So a stupid question: is there any Lie group behind this Lie algebra?
Yes, the Lie group will appear, I think, in the next chapter. Next slide, or in 2 slides. Just that, you know, I gave a rather abstract definition. I want to firstly show that, okay, we have two important the algebras, and they are really nicely described in terms of Lagrange dual coordinates. And as you wish, we can jump from Lie algebra to Lie group, and it will act locally on our space X, and of course will be generated by elements of GS infinitesimal generators as vector fields, and it would produce for us two important groups. One is BX and one is GX, and this notation is not accidental. This BX should ring a bell and remind you of the group B of P defined in the realm of probability. And what is really exceptional for this structure, which is purely canonically geometrically defined, is that, okay, we have the short exact sequence. The GX is the extension of BX, and this quotient is always one-dimensional, but this sequence does not split unless we fix potential, the information potential, because each fixing of this potential splits this exact sequence. A similar thing may be observed in probabilistic setting, because if we have a chosen measure P, we get the splitting that I wrote on the diagram, that we have B semi-direct with Q plus. And if we didn't choose this measure P explicitly and only just wander around in the realm of equivalent measures to P, then we again would get a short exact sequence that will have here the Bayesian group. Here would be this extension of Bayesian group, which shall be called the reinforcement group, and it would here have one-dimensional group, and this sequence would split exactly. Each splitting of this sequence will correspond to choosing a different equivalent probabilistic measure. Okay, so in the realm of probability, we got a morphism of at least these Bayesian groups through pullback via our morphism pi. And here, similarly, if we are given a morphism in our category Hess through affine surjection and write it in coordinates like this, then it would induce Lie algebra homomorphism between algebra H that is the Lie algebra of GY and G that corresponds to GX, and we have explicit formulas for it. And what is really, really fascinating for us is that the subgroup of the group GX that comes from the group BY and our monomorphism phi acts in a remarkable way, i.e. it acts perpendicular transversals to, the orbits are perpendicular transversals to the fibers of this F given here. And what is the most important thing, this property is gauge invariant. So it doesn't matter which one of the information potentials we choose, this geometric structure will always be there. So now we jumped in this geometric picture to something that looks really familiar. Because previously here we had synthesis of probability measures and here group actions, and now we have pure geometric objects. But now the time came for the last thing that I mentioned in the beginning, that is absent, i.e. the so-called James principle. So James principle simply states that, okay, these two information potentials are obeying this principle. Of course, here should be Ix and here Iy. So the potential in the codomain of F should be exactly the its values should be exactly the minimums of the potential on the domain when this minimum is calculated on fibers of our morphism F. What James' principle truly adds to our structure is a section for this morphism F. It is noted like usual by S, and it's simply defined as the argument minimizing the information potential Ix. It is a proper definition because Ix is the strictly convex function. And what additionally is satisfied by this section S is that with respect to this morphism phi of our groups, it is equivariant, it is an isometry.
So, Lukasz, I don't understand this notation. What does ARG mean?
Argument minimizer.
What is it?
So it's the X such that by
Yeah.
Oh, okay. Okay, fine.
Perfect. Okay, and these sections S coming from James' principle from here exactly coincide with the local orbits of our before mentioned group, and they, because of that, they are again all perpendicular to the fibers of F and equivariantly isometric too. Why? I am really thankful for the picture that my supervisor managed to create. I don't think I would be able to do something as good as he did in LaTeX. On board, we both created it many times, but you can see that when we have here space Y and here the space X, we have fibers of F here drawn horizontally because of what we did before introducing James' principle, having this phi and having the action of this normal subgroup by here, and having these dashed lines as local orbits of this action, we can see that, okay, even before incorporating James' principle, this geometric reality already exists on X, because we have one foliation given by fibers of F, and we have another foliation given by these actions of phi ui, and what choosing fixed information potential does, plus incorporating James' principle, is that it, when it comes to formulas, gives us S, but when it comes to geometric reality, it simply picks out of this whole foliation one orbit that the space Y is being embedded as in X. And independently of what potential exactly we would choose, each of these orbits behaves the same from the geometrical point of view. So to come back finally to this picture with our final structure, when we have this Hessian geometries here, with group actions here, with morphism F from one Hessian structure to another, inducing the group homomorphism here, and incorporating James' principle, creating this section here. The only remaining question is, okay, but what's the connection with probabilistic reality? Well, the answer is that if we restrict ourselves to finite space of elementary events, i.e. omega, when omega is a finite set, then these simplices that we assigned as spaces of probabilistic measure satisfying something will truly be finite dimensional simplices. So they would not only have a natural topology, they would have natural stratified smooth structure. And using the Kullback-Leibler divergence as this strictly convex stratified smooth function, we would get our information potential, and here we would get the Fisher-Rao metric. Either way, this Kullback-Leibler divergence may be viewed as a functor from this category where we reached through solely probabilistic reasoning, that we only had this simplest of measures without any topology and nothing more than some group action, and it gets functorially mapped to this Hessian geometry, and not only the simplest gain the Hessian metric and information potential here, but also the groups themselves are carried on appropriately, i.e. the B of P group B is mapped to Bx group, and the action of this positive rational numbers component is embedded into the action of real positive numbers that happens here when we fix an information potential, this group splits into a semi-direct product. Because it's 5 to 6 and Roosberg wanted to leave at 6, I'll just mention that if anyone is interested, I've put in at the end of these slides an example of how the Hardy-Weinberg model of Mendelian genetics fit into this kind of formalism. Just 3 or 4 slides of some calculations and explanation, but because of the lack of time, I'll leave it to the people that are interested. Then maybe not as homework, but if anyone would like to take a look, they're quite welcome to do that. And with that, I'd like to thank you all for attention and finish for today. Hope I stuck more or less to time. So I have no idea when exactly I did.
You're well below 90 minutes. So.
That's for sure, but I was aiming for 45.
I will take a picture of these.
But are we done? Should I stop recording?
Yes, I think so. Unless anybody has questions that want to have it in the recording.